Chapter 3 is all about bonding. We're going to look at ionic bonding and covalent bonding as we go through this chapter. Remember to keep a periodic table handy as we do this because the periodic table helps you understand bonding, and you will need to use the periodic table when you take your test and try to do problems like what we're going to be doing in this chapter. Atoms will bond to each other. When you bring two atoms close to each other, the electrons in one atom are attracted to the nuclei of the others. What happens from this attraction is the basis of bonding. Sometimes we see electrons are exchanged, and sometimes we see electrons are shared. When we look at what happens with atoms, we find that all elements are reactive except certain ones, and those are the noble gases. That's the last column on the right in the periodic table. They're also called inert gases because they don't undergo reactions. Noble gases have a very stable electron configuration. They all end, except for helium, end in P6. They all have an S2P6, except for helium, have an S2P6 outer shell. No, they have no electron affinity. They won't take extra electrons on, and they have the highest ionization energy of any elements in their period. They also have the smallest size. You can look at them as being a very hard golf ball, hard to take anything off it, hard to put anything on it. Other atoms tend to be more polarizable, meaning they can have electrons withdrawn, and they often will accept extra electrons. We look at them as being much more malleable or easily changed. The electron structure of the noble gases are shown here, and elements that are nearby the elements shown will react in such a way that they get to the electron structure shown for the noble gases. That means hydrogen will try to react in such a way that it attains a 1s2 electron configuration. Lithium will try to react in such a way that it gets the helium 1s2 electron configuration. Fluorine will try to react in such a way that it gets the S2P6 arrangement of neon. Sodium will try to react in such a way that it gets the S2P6 arrangement of neon. Now, realize that we're not talking about protons being changed at all. These atoms do not become noble gases. They still remain the same element. It's just their electron configuration becomes like that of the noble gases. We say that the electron configuration becomes isoelectronic with the noble gases. Those elements still retain the same number of protons that they had before, and so they still remain those elements. Their electron configuration is what changes. So, if fluorine gains an electron so that its electron configuration is the same as that of neon, it still is fluorine, but it has a -1 charge. So what we find is that atoms have greater stability when they change their electronic configuration so that it matches those of the noble gases. So hydrogen, lithium, and beryllium try to attain an S2 configuration, and the rest of the representative elements try to get an S2P6 configuration. Examples of this would be lithium reacts by losing an electron to become S1s2. Fluorine reacts by gaining an electron to become 2s2. Now, when these atoms react, there are two different ways that they can react. they can either gain and lose electrons to form an ionic bond. In an ionic bond, one atom transfers an electron to another atom. In a covalent bond, atoms actually share electrons to attain the stable electron configuration. Of course, nothing is ever black and white. You always have some gray areas, and most bonds actually have both some ionic character and some covalent character. To classify a bond, what we usually do is look at the atoms that are in the bond and classify them as metals or nonmetals. If the bond is between a metal and a nonmetal and they're far apart on the periodic table, we consider the bond to be ionic. If the two atoms are close together on the periodic table and it's a nonmetal with a nonmetal, for instance, carbon with oxygen or even carbon with hydrogen, we consider that to be a covalent bond. The bonds of atoms other than those, let's say atoms that are close together on the periodic table but are metals and nonmetals, aluminum maybe to phosphorus, those atoms are close together and you have a metal and a nonmetal, but they're so close that they're not different enough to transfer electrons, and we really consider them to be covalent with a lot of ionic character. But we're not going to worry about that. I just want you to know if you have a metal with a nonmetal, it's an ionic bond, and if you have a nonmetal with a nonmetal, it's a covalent bond. We've already looked at ions, cations and anions, and we know that they have charge. Ions are atoms with charge. They've lost or gained electrons. You have to remember, the key thing in this is that it's the electron numbers that are changing and not any protons or neutrons. So when electron numbers change, you have a change in the charge on the atom, but the atom still remains the element that it was before it lost or gained electrons. Now we're going to look into the formation of cations and anions. In order to understand a reaction arrow, I've given you these simple examples down here. A reaction arrow is basically a time sequence. So if we look at this example of a pregnant woman, arrow, reaction arrow, and then we have woman plus baby. Beforehand, we have a pregnant woman, time elapses, and then afterwards we have a woman and a newborn baby. Same thing with a sperm and an egg. Before, you have a separate sperm and egg, then time elapses and you have a zygote. Let's look at this the same way now with an atom. Beforehand, we have a neutral carbon atom. There are 7 neutrons, 6 protons, and 6 electrons. Time elapses, and what happens is the carbon atom loses an electron, so now it has a positive 1 charge. It lost an electron, so now its charge is positive. The electron is separate from the atom. We can form an anion by taking an extra electron and adding it to an atom. So here is a neutral carbon atom. We take an extra electron, time elapses, and now the extra electron is inside the atom forming this anion. There is an extra electron on that atom, so now it has a -1 charge. Almost any charge can be forced onto an atom. However, some charged states are high in energy and unlikely to occur, and some are low in energy and likely to occur. We've already seen that some electron configurations are stable, and when ions change and attain a stable electron configuration, you have a lower energy ion. Whether or not an atom will lose electrons to attain the S2P6 arrangement or gain electrons to attain the S2P6 arrangement depends on whether or not it has a high ionization energy It does not lose electrons easily, and a high electron affinity, it wants to take on extra electrons, or that would be the atom would gain when you have high ionization energy and electron affinity, or loss would occur when you have low ionization energy and low electron affinity. So we look both at electron configuration to see how many is needed to attain S2P6, and we look at whether or not they have high ionization energy or electron affinity to see whether or not they would lose or gain to attain S2P6. Now the common charges that we see are +1, +2, +3, -1, -2, and -3. We do not see very often a +4 or +5 because that's a lot of charge on a tiny volume of just a little bitty atom. Now, when ions form, it happens together. You don't have atoms spontaneously losing electrons. Something has to pull it off the atom. And free electrons just don't spontaneously occur. They're very high in energy and don't float around when there's matter around that it can stick on. So what happens for ions to form is that you have to have two atoms together, and one has to be able to pull an electron off the other. And what we find is atom A might pull an electron off atom B because atom A actually has a lower energy place for an electron than B has. Let's look at an example. If we bring lithium near a fluorine atom, lithium has a very high electron affinity and a high ionization energy. This means it's very difficult to remove electrons from fluorine, but fluorine will pull extra electrons onto itself well. On the contrary, lithium has a low ionization energy and a low electron affinity. It is very very easy to remove electrons from it. It has a low ionization energy, and it doesn't really pull extra electrons onto itself. If I look at fluorine, it has an extra place for an electron, and if it adds one electron, it becomes S2P6. Lithium has an outer shell of 2s1. If it loses that one electron underneath, it has a 1s2 of helium structure. So losing one electron from lithium will bring it to a stable electronic structure, and gaining one electron on fluorine will bring it to a stable electronic structure. As a result, what happens? You bring the two near each other, and when they get close together, the fluorine starts pulling on the lithium electron. The electron then pops off of the lithium and jumps onto the fluorine, making a fluorine anion with a -1 charge and a lithium cation with a +1 charge. These two ions now have opposite charge, and that opposite charge causes them to slap together and be attracted to each other and form an ionic bond. Metals are all on the left-hand side of the periodic table and so have low ionization energies. As a result, they tend to lose electrons in chemical reactions. So when they react with nonmetals, they give their electrons to the nonmetals. The number of electrons lost depend on how many electrons they have in their outer shell. The metals lose the electrons that are in their outer shell. So the alkali metals, which have an outer shell of S1, lose that one electron and attain a natural ionic charge of +1 when they react. When alkaline earth metals form compounds, they have an outer shell of S2 and they lose both of those electrons to get a positive 2 electronic structure. The transition metals all lose a variety, and we're not really going to go into the how they lose their electrons. There are only a couple of metals in the transition block that we're going to actually investigate. So we're not going to worry about those right now. The family with aluminum have an S2P1 outer shell, and they lose all of those electrons and get an S0 arrangement for 3+ charge on an aluminum ion. Tin, which it has a symbol of Sn, and lead, which has a symbol of Pb, can lose 2 or 4 electrons to get a positive 2 or a positive 4 charge. And that the reasons for that we're not going to really go into right now. The nonmetals have high ionization energy and do not lose electrons. They have high electron affinities, and so they gain electrons. To become isoelectronic with inner gases, they gain the number that will bring them to S2P6. The halogens gain 1 electron so that they will be S2P6, so their natural ionic charge in compounds is 1-. Oxygen has an outer shell of S2P4, and its family gains 2 electrons to go to S2P6. Elements in that family have a natural ionic charge of 2-. Now, I've been giving you the charges that these elements have, and I put them in this periodic table here so that you can see how the pattern is within the periodic table. I want you to realize and pay attention to this little thing that I'm telling you, as the charge is only on the atoms when they are in compounds. When the atom is in the elemental state, for instance, when lithium is in pure lithium, it has no charge. When oxygen is in pure oxygen, it has no charge. These charges are only when the atoms are in compounds. You can see the pattern that we have. The first column has 1 positive as the natural ionic charge for when they're in compounds. Second column, positive 2. The halogens, -1. The column with oxygen, -2. I've put some other charges here for you, and you can use them when doing problems. The elements that we're going to focus on will be the first 2 columns in the periodic table, the last 2 columns in the periodic table, and we'll do a little bit of chemistry with tin right here and lead right here, zinc, silver, cadmium, zinc is here, silver, cadmium, and this is aluminum. And there's some others over here. For instance, this is chromium, manganese, iron, cobalt, nickel, and copper. The only transition metals that we will use regularly will be iron and copper. Know the charges for iron and copper, these 2 elements right here. Right here I have listed for you the ions that you are expected to know in an exam. Column 1, column 2, the halogens, the column with oxygen, and iron and copper. Focus on knowing these charges and practicing problems with them. You can practice problems with other elements, and it will be useful for you understanding the principles, and it will help you understand what you're doing on exams better.